Hello students, today my topic is double sideband suppressed carrier, also known as DSB-SC. Already we have gone through few topics of amplitude modulation. You have already known that how that amplitude modulated waveform should be look like and how it is generated and demodulated also. So our next topic is double sideband suppressed carrier, where we are going to show you that we are going to suppress the carrier for saving the power and improvement of the efficiency, and only two sidebands will be transmitted, which will carry the information or the actual message. Now assume the message signal MT, which is I have given like this, and waveform of message signal, baseband signal, and next a carrier signal CT. CT is given as AC cos 2 pi FCT, where I have already described that AC is nothing but the amplitude of the signal, and this FCT is contains the frequency part of the signal, that high frequency term. So I'm giving you the general expression of DSB-SC, which is given by the multiplication of both my message signal and the carrier signal. So the final signal, DSB-SC signal, is DSB-SC is given as MT into CT, where CT is given as AC cos 2 pi FCT. The final equation is coming like this: AC MT cos 2 pi FCT. So the generation of this DSB-SC can be done by a product modulator circuit, where we can see that in the input we are giving two signals, that is baseband signal MT and the high frequency carrier signal AC cos 2 pi FCT, which is generating my double sideband suppressed carrier. And how this envelope is generating, as the cos term is taking as the cos part is having both the positive and negative frequencies, so in that way it will getting multiplied with my message signal. So the positive envelope and the negative envelope is generated, and we are getting this kind of DSB-SC modulated signal. Now let's come to the spectrum of this double sideband suppressed carrier part. To plot a frequency spectrum, we already have discussed that we have to take the Fourier transform of my entire signal. So here we have to take the Fourier transform of this signal, which will give me this SF. SF will be written as AC by 2 MF minus FC plus MF plus FC. Here you can see I have drawn that message signal frequency spectrum as this way. Next, the carrier signal frequency spectrum, which is having two part, FC and minus FC. Here message signal is having two frequency part, plus omega m minus omega m. And so finally I am getting my double sideband suppressed carrier spectrum in some this way, where you can see that AC MT cos 2 pi FCT, after doing the Fourier transform, we are getting both the side. This is my FC and my two sidebands, FC plus omega and FC minus omega, which is centered around FC, and on the negative side, which is the mirror image side, it is created on the around the minus FC side. This is minus FC plus omega and minus FC minus omega. So here I have made this FC in dotted lines to show you that the carrier has suppressed over here, and the envelope, the size of this envelope I have done here, that is half of AC by M0. By M0, if I'll take F is equals to FC, F is equals to FC, then it will become FC minus FC is equals to M0. So AC by 2 M0, AC by 2 M0. So from this spectrum representation, we can derive the bandwidth formula, which is nothing but the difference between the higher frequency and the lower frequency. FC plus omega minus FC minus of minus omega, that is plus omega. So FC will get cancelled. So 2 omega, that is the twice of the message signal, will my message signal frequency will be the bandwidth. So there is no change of this bandwidth representation. That means in full carrier, double sideband full carrier also, the required bandwidth was 2 omega, and here in double sideband suppressed carrier also the bandwidth, required bandwidth is 2 omega. So in term of bandwidth, we cannot get any benefit. Let's see what is our next topic, that is a single tone double sideband suppressed carrier. That is, I have taken a example of the message signal. Previously I have derived that entire term as taken empty only, assuming message signal as empty. Here I am giving the message signal a example. Why it is single tone? Because my message is consisting of one frequency term, only one frequency, that is 2 pi fm. 2 pi fm, single frequency, and that will get multiplied with my AC cos 2 pi fct, which will give me my final DSB-AC signal, ACM cos 2 pi fct into cos 2 pi fmt. No plus, this will be minus, sorry, this will be multiplication. So that will give me this ACAM by 2, this cos A cos B formula, which will give me cos A plus B cos A minus B. We have already seen this kind of derivation in AM generation also. So ACAM by 2 cos 2 pi FC plus FM FC minus FM. You can remember those things. So this will give you the upper sideband side and this will give you the lower sideband side. That same way I have drawn the spectrum, and this is the envelope side, these are the sideband amplitude, that is given as ACAM by 2. Next I am coming to the total power of DSB-AC. As we have seen that in DSB-AC there is no carrier, only the sidebands are present. So the total power of my double sideband suppressed carrier will be only the power of the two sidebands. Power of the one sideband can be derived as ACAM by 2 whole square divided by 2R. So that will give me AC square AM square by 8R. So if I take the total power, then it will be twice of this power. So 2 into this will give me AC square AM square by 4R. So that is the total power of a double sideband suppressed carrier. Next, coming to the modulation efficiency part, which is already we know the formula is given as neta is equals to total sideband power by the total power. That means in the total power, what is the contribution of my sideband power? So here already we know my total power is the sideband power. So sideband power by total power is nothing but it will give you 1. So 100% efficient transmission can be done where 100% power only taken by the sidebands. So in the term of efficiency, we can see some improvement than normal DSP full carrier to double sideband suppressed carrier. Next, how to generate a double sideband suppressed carrier. That is a circuit or the modulator circuit of the double sideband suppressed carrier, which is nothing but a ring modulator circuit. Here we can see that 4 diodes are connected in a ring position. So that is why this circuit is known as ring modulator circuit. And in the input side we are giving the empty, and this is a transformer, and here it is in 1:1. And on the outside also there is another transformer. The coupling of this transformer is written over here is 1:1. What does this 1:1 means? That means it is neither step up neither step down. The whatever the direct voltage we are applying over here, that voltage will be transferring directly on this coupling. Next we can see we will assume this. Here I am applying this carrier signal or the carrier voltage. First case, we will take the entire circuit, how the circuit will be operating. We will be breaking it in two parts. Once I will put this carrier signal as a positive signal, and on the second part I will take the carrier as the negative signal. So let's come to this operation. Now we can see this is my message signal, baseband signal, and the carrier I have taken a pulse train, and that is the final double sideband suppressed carrier which is generated. So in case 1, when CT is positive, when my CT is positive, this time only D1 and D2 are forward bias, and so this will be a short circuit and this will be a reverse bias, so this two will be a open circuit. So that's what only I have written. D1 D2 will be forward bias, act as a short circuit, and D3 D4 will be reverse bias and act as a open circuit. That's why the final diagram of the circuit I have drawn like this way. This I have made short circuit, and here D3 D4 there is open circuit. So what I can see, as I have told, whatever the voltage I am applying, it will be coming to this next transformer winding of this transformer, secondary winding. So whatever the voltage, that is plus minus positive negative, here also it will be become positive and negative, and the same voltage will be coming here, and this will be transferred to my outside also, outside of the transformer, which is noted as Vt is equals to Mt. Now on the case 2, when my Ct is negative, that is when we are getting the negative pulse of this carrier, that time this D3 D4, if this is negative and this is positive, that time what will happen? This positive signal will be passing through, suppose this is positive, so this positive signal will be passing through this D4, and from here also this is negative signal, so, and here also this positive signal will passing through here D3, so that will make my both D3 and D4 forward bias and D1 and D2 reverse bias. Clear? And when D3 and D4 will be forward bias, that time that amount of current will flow will be, the magnitude and polarity will be same, and they will cancel each other. So that is why this circuit is redrawn in this way, that D1 and D2 will be now reverse bias, so there is no D1 and D2, only D3 and D4 path are short circuited, and now whatever the message signal I am applying, it is coming to the secondary winding of my transformer. Now that voltage is coming in this way, opposite polarity, and that will be passing here only at the outside of this secondary coupling, secondary winding. So now Vt is equals to minus Mt. So that only shown in this diagram. When my Ct is positive half cycle, that time positive part of my message signal has passed, but when my Ct is having the negative half cycle, that time we are taking the negative part of my message signal. Fourier series expansion of the carrier, this is a pulse train, right? So for the pulse train, Fourier series expansion we need to take, and that will be contains lot of odd harmonics. So that is given as Ct is equals to 4 by pi summation of n is equals to odd harmonics, that is n could be 1, 3, 5, 7, etc., minus of 1 n minus 1 by 2 by n cos n 2 pi fct. And from this representation of the carrier, we can say when Vt is passed through the band pass filter, which is drawn over here, when Vt is passed through the band pass filter, tuned to Fc, the output will be desired DSB AC signal. That means if n is equals to 1, that time only my BPF will pass that signal, because n is equals to 1 means it will become 1 minus 1, it is 0, so all 0, so it will become cos 2 pi fct. No extra harmonics are there. If it is 3 phi 3 n is equals to 3, then fc will become 3 fc, but I have written over here that Vt is passed through the band pass filter, which is tuned to the fc. Tuned means that band pass filter cutoff frequency will be fc. If it is more than that, then it will reject those higher frequency signals. So that is why if n is equals to 1, then only it will get passed, otherwise it will get rejected. So finally whatever the ST we are getting, that is 4 by pi mt cos 2 pi fct. And already we know the DSB-AC signal expression, which is nothing but the multiplication of the message signal and the carrier signal. So here also we are getting the same part. So that is how we are generating a double sideband suppressed carrier using the ring modulator circuit. And finally, we will come to the last topic of this lecture, that is the demodulation of double sideband suppressed carrier by synchronous detection. For double sideband suppressed carrier demodulation, here I have written the term synchronous detection. Synchronous means whatever the circuit we are using, here we will be applying one carrier signal which need to be synchronous with the carrier signal present in my double sideband suppressed carrier. So let's see how does it work. So here is the double sideband suppressed carrier signal, which is already we have explained ACMT cos 2 pi FCT, and here is the local oscillator generated carrier signal AC cos 2 pi FCT. It is coming to a multiplier circuit, then it is going to the low pass filter, and finally it is generating the desired message signal or MT. Now I have taken two cases. One case is, assume that local oscillator output is perfectly synchronized. There is no error, no phase error. So that is why I have written AC cos 2 pi FCT. AC cos 2 pi FCT. So multiplier output will be SDSBST into the local oscillator output, which is nothing but this AC square MT cos square 2 pi FCT. So AC square MT into 1 plus, that will come in the formula, and I will get this value AC square MT into 1 plus cos 4 pi FCT by 2. So my low pass filter will be giving the output as AC square MT by 2, only this part. And it will, as it's a low pass filter, it will be giving the low frequency signal, and the higher frequency signal will be get rejected. And finally this term can be passed through an amplifier circuit to generate the original message signal. Now coming to the case 2, that is if there is this local oscillator output, this carrier signal, if not perfectly synchronized with my input carrier signal, then how it will be. So if there is a phase error, so my local oscillator output is AC cos 2 pi FCT plus phi. So no phase synchronization. So the multiplication output will be like this way: ACMT cos 2 pi FCT into AC cos 2 pi FCT plus phi, where ACMT AC square MT cos 2 pi FCT into 2 pi FCT. So cos square 2 pi FCT is there. So which is giving this 4 pi FCT, and plus AC square MT by 2 cos phi. So finally we are getting this output from the low pass filter, as this contains my low frequency signal of message. So this will be passed through my low pass filter, and this will get rejected. Now if phi is equals to 60 degree, cos 60 is equals to half. So this message signal will become AC square MT by 2 into half, so AC square MT by 4. Where is no problem, it will get passed through the amplifier circuit and it will generate my message signal. And if phi is equals to 90 degree, then this low pass filter output will become 0, as cos 90 is equals to 0, which is known as the quadrature null effect. So for reconstruction of MT, phi should be constant to avoid this kind of null effect. What measures we can take? For reconstruction of MT, phi should be constant. To maintain phi to be constant, additional circuitry has to be used, which makes synchronous detector more complex. I hope you have understood today's topic, which is double sideband suppressed carrier, and I will be also sharing this hard copy with you. Thank you for listening to this.